All right, so I am Joe Spisak. I'm here to talk about the rise of machine learning. And so who knows about machine learning? Who's heard of it? I think everyone's probably heard of it. Who works on it today? Cool, okay. But I know you, okay. And okay, so anyone consider themselves an expert in machine learning? Damn, because I'm hiring. So I need engineers. I'm hiring especially female engineers. Actually, I'm hiring 2 right now. So I'm kind of going to talk about the motivations of machine learning, but it's not as sexy as it sounds. Actually, it's cool, but there's like a lot of crazy stuff that goes kind of underneath it, and a lot of hard work. So I'm going to talk about who I am, why I'm talking about machine learning, what is machine learning, why now? Because there's machine learning has actually been around for a really long time. People have been working on this stuff since even like the 50s and 60s. You'd be amazed some of the algorithms that are even today being used. So really, why now? What are the components and stages of machine learning? Because there's, it's not like a magic algorithm. You throw a bunch of data in, all of a sudden you get something out, and magically you can infer or recognize cats and dogs in pictures. There's actually a whole bunch of stuff that goes on underneath, and I'll kind of point you guys to some of the more popular algorithms, some of the more popular things that people use for various stages. What are the packages and frameworks that are out there to get started with, and kind of which one to get started with. I have my preferences, of course, but people know different languages and they want to tackle different problems. So there's different packages for all types of different things. And then how do I get started, right? I mean, there's motivations, there's different things you can get involved with. There's videos, there's classes, so I'm going to kind of go through that as well. So who am I? So I currently lead strategy and cloud engagements for Intel, for the visual cloud computing group. I'm, like Mary, I'm also a media person. I've been doing media for, not to date myself like she did, no, I'm not that old, but I've been doing it for 15, 16 years now, and I've been working all the way from the mobile side of things to broadcast. For the last 3 years, I've been working on cloud. In fact, as far as some of the experience I have, I've 2 exits. One actually to Facebook out of Intel that we sold a cloud media team over to them with a bunch of IP through a company called Quickfire Networks. Quickfire did one of the TechCrunch Disrupt. They actually won one of the top prizes last year for some of the work that we actually did at Intel, which is cool. My education, I've done some innovation and entrepreneurship work at Stanford. I have an MBA and a master's in finance from Denver, and I'm also an engineer. So I'm a bachelor's of electrical and computer engineering from Michigan State University. Go Spartans. My hobbies are programming, which is where I spend most of my time kind of playing around. I'm also an ice hockey player, and you can see my future coach chick there, Julia. She's 17 months old now. And she will be a coder and will be an engineer likely. Okay, so let's talk a little bit about taxonomies. So this is kind of a confusing topic for a lot of people. People misuse terms all the time, right? They say, so what about data analytics? Is that machine learning? What about visual understanding? Is that machine learning? Cognitive computing, that's got to be machine learning, right? Well, it's yes and no. Right, I mean, if you look at cognitive computing, you think about brain-inspired computing, what comes to mind for me are things like neuromorphic computing. So really trying to mimic the way the brain operates and use that as something to translate into some type of hardware. So there's a lot of startups right now working on brain-inspired or neuromorphic computing. It's actually quite a hot area. Visual understanding is really the ability to understand media, really. So like images, video, speech, natural language. That's kind of the umbrella term for visual understanding. But that could use machine learning, but it could not. So traditional computer vision in the past hasn't used machine learning. It's actually used a lot of handcrafted features, a lot of kind of insight into how the objects that you're trying to classify. For example, if I'm going after license plates on cars, because I want to make sure that I'm in China, for example, it's a problem with fraudulent license plates. I want to craft the features in a certain way. So I'm not maybe using machine learning there, but you could, of course, use machine learning, various types of it. Of course, data analytics, that's another big umbrella term that kind of associates with big data, with the Spark and Hadoop world. And then once you get into the machine learning side of things, which could be applicable to all of these, that really is the autonomous computation, basically algorithms learning from experience, or in this case, data. And we'll define different types of data. And when you drill down into machine learning, there are lots of algorithms, as we'll talk about in a couple of slides. Deep learning is the one that's kind of near and dear to my heart, and I've been working on it for almost 3 years now, and it's a really, really cool stuff. But really, it's about using layered or hierarchical approaches to solving problems. And as you move further and further through layers of deep networks, you tend to find more interesting things out of data, and more interesting representations, more. In the case of finding faces, you will actually start to find actual faces instead of just edges and so on. And if you're interested in that, come talk to me afterwards, because I'd love to talk about it. And one of the more popular types of that is called convolutional neural networks, and this is actually used by Facebook. It's used by Google. It's used by most folks today to do things like image recognition, so your Google image search uses that. There are other variants that are used for speech, like Siri or Cortana, use these types of networks. And then once you actually drill down to the kind of sub components of these machine learning algorithms, you will train a model based on a lot of data, depending on, of course, what kind of data it is. And then you will deploy that model, and that's when you score it. And scoring could be classifying an image, it could be inferring from the data set to predict something, and so on. So if you actually look at what machine learning is, I grabbed Tom Mitchell's, of course, kind of seminal quote over at CMU, Carnegie Mellon. A computer learns if its performance improves with experience. And in this case, the way he defines experience is data. So if I take my algorithm, I have a bunch of training data. And training data in data science or machine learning is like to quote Andrew Ng over at Baidu, it's your fuel, right? It's really what drives your accuracy, your algorithms. It's how you learn. So the fact that we have huge data today and these days with everything happening, it's really kind of pushed a lot of this forward. I'll talk about that in a second. But your algorithm, this is just a generic block diagram, so it could be one of hundreds of different types of algorithms. I will train based on that training data. I have some then error that's generated. So maybe based on the training data, my algorithm actually accurately predicts maybe say 80% of that or 70% of that. From there, I say, am I happy with that? Likely not. So what I'm going to do is typically either add data or modify the algorithm. In other words, I will adjust some weights within my algorithm or within the model. I will do some training again. I will iterate until I'm happy with it. And then I will do something like a cross-validation step where I have a set of test data. So I might have a big pool of data out here from the beginning, and I want to separate those into training and test. And once I've trained my model, I will run the test set, and that's kind of like taking your model and putting it out in the wild and saying, okay, now that I've trained it on this set of data, what happens when I introduce new data? And it will either look great, or it might not look so great, depending on the domain you're talking about. But it could be good. So, but it's never going to be obviously as high as the training data because it is new data. So it's probably going to be somewhere, in between not so good and in where you're training. It'll definitely be lower than your training data. And if you're happy with your test error, you go ahead and deploy the algorithm, deploy it into your service, whether it's something like a click-through rate prediction, like the web guys use, or PageRank, or some of these other algorithms that these guys are using, like Microsoft and Google. If I'm not happy, of course, I add more data and I keep training, and that's really where everything's kind of happening today with all the big data. So if I jump into the different types of machine learning, so these are very high umbrella terms. I will get very, very concrete here in a couple slides. But if you look at supervised learning, there's unsupervised learning, then there's reinforcement learning. I'll take them one at a time here. So a great example of supervised learning is when I have labeled data, which today, for example, we have more labeled data than we've ever had. So Fei-Fei Li over at Stanford really started ImageNet. If you ever get a chance to go Google search ImageNet and learn her story or watch her TED Talk, it's fantastic. But she went and created this database of images, millions of images that are pre-labeled, which sounds trivial, but it's actually really powerful. And so really with supervised learning, an example here is, of course, an email filter, a spam filter. Every time you have your Gmail account and you find a spam, you classify, you click on that button that says, this is spam, what the heck is this doing in my inbox? That actually feeds it back to Google, and they add that to their training set. And so next time they train their algorithm for their spam filter, it gets more accurate, right? So their accuracy right now is like 5 nines or even higher on pulling spam. I haven't actually seen spam in my inbox and on my Gmail in, I think, years, actually. It's pretty awesome. So, that's an example. So basically I have an X and a Y pair, I have a piece of data, and I have a Y label for it. And I'm using that, I'm training on that to predict what new X's would be like, right? Unsupervised is similar, but I don't have labels. I have just a bunch of data. I might have unstructured, unlabeled data. I'm trying to discover new patterns. This is actually quite useful in the medical space, where I don't know what the heck is going on in some of these images. I can't label them, it's just new information. And in this case, you can see I'm clustering. So there's all kinds of different clustering algorithms, density-based, could be density-based, it's used especially in medical. But I'm really trying to understand patterns and learn new things. And there's been research like crazy about this. A lot of the Google papers, for example, that have been released, they'll actually use, say, a combination of things, and they will train on supervised data, so it's labeled data, but then they introduce new information, new things, and actually I think one of the papers, I forget which one it was, they discovered cats, right? They're able to discover based on all the images. It wasn't one of the original categories from the supervised learning training set, but it was a bunch of new images that they applied to the algorithm that weren't labeled, and they were able to discover new things. So that's really where unsupervised comes in. Reinforcement learning is also kind of on the bleeding edge of research at this point, and that's really about policies. So I set a policy or a set of policy rules. It's really a rule-based type of algorithm, and it's being driven a lot in autonomous vehicles, for example. I always point to the DeepMind paper and the work over there, another acquisition of Google. They taught an algorithm to play video games, and it actually is much better than humans. And really, the one rule was the score has to go up. so if the score goes up, then the policy, it's good, or if your algorithm is following the policy. And so really what the algorithm was doing, it was manipulating pixels, it was moving the character in certain directions until it found patterns where if I do this, the score goes up, and it followed that rule, and it iterates and iterates, and it learns over time that what it's doing is actually doing the right thing and actually adhering to the policy. And so that's, it's being used in robotics. If you look at what Tesla is doing with their manufacturing right now, reinforcement learning is actually a big piece of that. So these are kind of like 3 umbrella terms, or umbrella types of machine learning. Now you get into all kinds of other examples. So why now? Why machine learning now? So if you look at, I kind of clipped a bunch of things, a bunch of headlines, right? There's things around Watson and big data and oil and gas. It's really an insane amount of data out there. So the cloud, and there's a reason why the cloud providers are they're on the leading edge of this, is because they're actually the one gathering the most data at this point. They will crawl every single website out there. They will continually crawl the internet. They will classify every single image out there. They will gather every piece of video, every piece of text, every bit of speech that's out there, and they will classify it, and they will use that as fuel to improve their algorithms. So this is happening. Robotics right now are hot. There's a lot of issues with fraud right now, with hacking. So people are looking at some of these algorithms to be able to detect some of these things, right? These hackers, for example. We can't possibly predetermine every possible path someone's going to take to hack into a system, whereas a machine learning algorithm could adapt over time and learn, right? Whereas we're very focused on, say, stopping one particular thing, and that's why your traditional your Symantec, your McAfee antivirus, it will update after there's been a threat. What you're talking about with machine learning is actually looking and preempting that ahead of time. So if we jump into the stages, so I'll kind of walk through this very, very quickly. There's a lot of information on these slides, so forgive me. Data selection. Data selection is kind of the first step. So, selecting the data, analyzing, what kind of data you're going to be using, and I'll share these slides so you guys don't have to read from here. But there's there's problems with that, right? There's, based on current algorithms or certain algorithms, you can only subset, or you can only fit a certain amount on your PC, for example, so you're gonna have to sample. There's data prep. I would argue actually that this is one of the hardest things in data science and machine learning is just prepping the data. These guys do what's called data wrangling, and that's cleansing and actually getting the data actually into a form that you can actually use it. Because I think there's a huge percentage of the data that's out there on the web today that's really unstructured. It's not in a really easily consumable format that somebody could just pull into their algorithm and really be able to use it and train their model. So that's why these public databases, these Creative Commons databases of say images like ImageNet or CFAR or the MNIST database is another one. It's a set of handwritten numbers. You can train on those. You can go grab those, and they're pre-labeled and they're very clean. The real world is not so clean, so so it doesn't quite work that way. So this is actually where you spend most of your time. Model selection. So what am I trying to do here? Am I trying to cluster? Am I trying to find these clusters of information or like neighbors of information? Am I trying to detect classify images as an example? So figuring out which type of model I'm trying to create, training the model, getting it to converge and getting it to an accuracy that's actually usable is the next stage. Evaluation. So have I verified that the trained model makes sense? Have I taken a bunch of images in the wild and found that I can actually classify at a good accuracy? And then deploying. So once you've done all this work and you've kind of gone through all the blood, sweat, and tears of actually creating your model, how do I deploy that? Do I want to deploy it on a client, for example, on a mobile device? Do I want to deploy it in the cloud? These are kind of the things that need to look at. So if I jump in here, talk a little bit about the descriptions, data selection. So again, what kind of data am I dealing with? Am I dealing with video? Am I dealing with audio and speech? Am I dealing with unlabeled data, unstructured text? Different algorithms and different techniques work better for different types of data. And one thing to note is everyone these days is looking at multimodal type of work. So they're looking at combinations of maybe images and text, for example, or learning text or creating text from images. So creating semantics from data, from images or video. That's actually quite hot right now. Data prep. Am I looking at reducing the dimensions? Some of the data out there, some of the problems that people are trying to solve, especially in the medical space. I was at the Stanford data science retreat a few weeks ago, and some of the people in medical, some of the research over there using machine learning and data science, they're talking about tens of thousands of features, sometimes even huge numbers. I mean, and that's really a data science problem. When you get into deep learning, you're talking about millions and possibly billions of features. So how do I, for example, transform or reduce the dimensionality of these? Do I use adaptive preparation? What are the techniques I use there really to prep the data? Model selection, what am I trying to accomplish really here? Am I trying to do a regression? Am I trying to find the relationship between two variables? Maybe. Am I trying to classify, for example? Am I trying to do clustering? So these are the types of kind of motivations that you're going to have based on what model type that you select. Of course, model training. So you could be doing deep learning. You could be doing graph, which for example, Facebook is built on a huge graph. So lots of data they have to train their graphs based on every click and everything you post to your Facebook page. Evaluation, talked about that. One of the interesting things that's happening going forward is things like online learning. So as you deploy a model, for example, it's not going to be perfect forever. Things are going to change. The world changes, and your model has to change with it. So there's something called online learning that people are looking at. There is model deployment. So how portable is it to other platforms? Do I look at ensembling, which means I'm using a combination of learning algorithms. Yeah.
Previous slide.
Yeah.
So you mentioned data prep takes about 70% of the time.
Yes.
Did you mention that you could use machine learning to prepare data
You could, absolutely. You can definitely train your own algorithm to do it for you. And that's really where, adaptive, automating that. There's something called the Amazon Mechanical Turk, which people use. People pay other people to go and do this for them. People want to make money. They want to go find data for them and label it for them. So there's,
so supervised labeling.
yeah.
But there are no unsupervised algorithms for training for cleaning up your training data.
There are some, yes, actually. People are researching that quite heavily right now, actually. So definitely, because it is a problem, right? Not all the data out there is labeled, so people are looking at how to automate that, how to create semantics from things automatically, so I can automatically label. So just think about the deaf, for example, and trying to create subtitles of just raw video instead of having to hand type that. You can automate that, and that's a huge area of research right now. So, okay, so let me get one level more concrete. So, who are the talented? Who are the people around that are working on all this stuff? So, of course, software architects, developers, PhDs in machine learning, data scientists, UX, UI experts. Data prep. Here's just a few examples of different things. Reinforcement learning again. There's crowd labeling, like I talked about with the Amazon Mechanical Turk. I won't jump into all these because I'm running out of time. But model selection. So I'm doing a rule extraction. I'm doing something like a k-means clustering, which will give me basically however many clusters of the data that I choose based on number k I choose. Am I doing classification? Is it binary? Is it multi-label, multi-class? Am I doing regression? Model training. There's, again, tons of algorithms depending on whether or not you're doing deep learning, for example, or you're doing graph. There typically, with any of these algorithms, tends to be some type of cost function that you're trying to optimize. So things like gradient descent may be used there. Which, if you're familiar with the chain rule in calculus, if you all remember calculus, it's very handy to know. Model evaluation, so, there's things like hyperparameter optimization there, which is almost like a meta problem that people are trying to solve with machine learning. It's like machine learning on top of machine learning, because there's all these nuisance parameters that people have to go figure out just so they can actually work on their real parameters that they're trying to create with the model. And that's where hyperparameter optimization comes in. There's metrics that people use. There's things like precision and recall, where I'm trying to understand how accurately I'm predicting, say, true positives or true falses. And then lastly, model deployment. And looking at applications, for example, there's recommendation engines, just as an example, as anomaly detections. If I look down here, ensembling, there's things like stacking, boosting, bagging. These are all techniques that people are using to kind of batch up a bunch of weak learners. For those who don't know what a weak learner is an algorithm that is maybe a little bit better than a random guess. So, so if you have a bunch of weak learners, then you can kind of ensemble those together and actually get a strong learner, right? Something that is much more accurate. In the end. And actually, on a side note, if you look at what Netflix does, and they used to do this competition, I'm not sure if they're still doing it or not, but they had a competition for creating a recommendation engine better than Netflix. And people were using something like more than 100 algorithms. This was just a few years ago, 130 algorithms combined to get it to a strong learner and actually better predict than Netflix own algorithm. So it's not just one algorithm to kind of rule them all. It ends up being a bunch of them combined. So, what are the frameworks and tools that people are using? And I work with everyone from Facebook to Google to a lot of our large companies and small ones, and they use a lot of these tools, right? They use open source. So this is all available to you guys as well. So things like R, which I use personally, Cafe out of Berkeley, Torch, Spark is a great one that does in-memory processing. It has something called MLlib, called a machine learning library. It has a great set of algorithms there. If you take the class at Stanford by Andrew Ng, I took several years ago, and he teaches it now through Coursera. Use something like Octave, Mahout, which is part of Hadoop. So there's a bunch of, this is just literally a small slice of what's available out there. There's tons, it's crazy. So, go play with some of these. So, I guess last question, or last slide. So what do I need to do to get started? I mean, I guess my advice to you. So pick something you're passionate about. So if you're passionate about ice hockey like I am, or you're passionate about children or and teaching or whatever you're passionate about, use that as your single focus goal. Machine learning is a tool. It's an algorithm or a set of algorithms. It's not something that you're just going to go and develop and be satisfied with. You want to have something that you can apply it to. So that's my advice to you. Number 2, brush up on your linear algebra and statistics. It's amazing how much I remember from undergrad engineering school, or don't remember, I guess, is more specific. But go brush up. There's tons in there. Just take a basic class or read a linear algebra book and learn about matrix multiplication, because that's seemingly the center of the universe these days when it comes to machine learning. And just brush up on that. Number 3, pick a language. So pick R, pick Python, and just start playing with it. Python's a great one. It's used everywhere. The packages are fantastic. I find for R, there's a ton of great packages that are community-driven. People are developing these great packages, and there's worked examples for all of them. Like an example, when you install R, it automatically shows you, their implementation for k-means clustering, which is an unsupervised machine learning algorithm. So, it's something you can go grab the code for, you can play with. It's awesome. Take a class, like I said, or 2 or 3, or, continue to learn. Stanford, Johns Hopkins, Washington, our great friend Carlos Guestrin over at Washington, he's teaching a class now from Dado and Amazon on machine learning. There's some great classes out there, and they're free, right? Just even if you don't sign up officially and take the tests and all that, just watch the lectures, play with the tools. You'll learn a lot. And lastly, just hack and play around. Like I always say, think like a child, because that's the way you learn. At least I do. I learn by doing, and this is really the best way to get involved and learn. It's really the place to start.
So you work with both R and Python. If you were going to do something that used a cluster, which would be the better choice?
They both have, honestly, there's no bad choice. I think my personal experience with R, I think every one of them has all the packages out there. I mean, even if you go into MATLAB, for example, people have written, say, k-means clustering or k-n, nearest neighbor algorithms for all of for different things. So yeah, you can't go wrong. It's all what you're comfortable with. I really like R because the IDE is really smooth. It's really slick, and it has really nice tools. Excuse me, I'm losing my voice. It has really nice tools for debugging your code and visualization and stuff. So that's all what you're comfortable with.
We have time for one more question.
Yeah. Yeah.
I'm ASIC design engineer. I work at Intel. So
That's
the
right.
question I have for you is just talk a little bit about hardware enhancements for system development happening in the field around automated making machine learning more cheaper.
Yeah, great question. It depends on which algorithm you're talking about. There's very highly vectorizable and parallelizable things like deep learning, where it's as it's probably from your question, it's a lot of matrix multiplication. So gem operations tend to dominate. There's things like speech, for example, where GEMV, a lot of matrix vector multiplication. But then there's a lot of other proxies, other things for some of these other data analytics, doing random forests and enhancements. I can speak from the Intel perspective publicly. We're investing heavily in FPGAs. You can use. We have some things like our Knights family for going forward that are targeted at HPC, but do machine learning really, really well. It really depends on the algorithm, because there are algorithms that benefit from single thread, but then there are ones that are very parallelizable as well. So really, if you have an embarrassingly parallel problem, a GPU, I hate to say that as an Intel guy, we don't, although we do GPUs, so sorry, but so GPUs can handle certain workloads, CPUs handle others, FPGAs give you a better kind of performance per watt, so they tend to be deployed in data centers more widely by some of our customers.
So do you see that you're able to push hardware forward by pushing your algorithms or enhancements for your algorithms? I'm assuming you're working on algorithms for machine learning. Are you pushing them back as well?
Yeah, definitely. Area very much focused for us.
Is the Knights family, do they have archivers?
Yes, actually they do. So we have a set of libraries called MKL, Math Kernel Library,
Yeah.
and it has interface to R.
Oh, okay.
So if you go to Revolution
Revolution
Analytics,
R, okay.
yeah, so that's all that connects right up, and you can program, basically call in MKL in R, and it will do all the heavy lifting underneath, because you can sit there and write AVX instructions on Intel all day long. It's really hard stuff, but we don't really think that's value added for somebody who's trying to solve a problem. So yeah, we've done that pre-optimization. So
Thank you so much, everyone. Thank you, Joseph.
sure.